Hello and welcome back to session 2 of our HYSYS series. If we haven't met yet, my name is Alex and I'm a process engineer. In the last session, we used the HYSYS line sizing manager to figure out the right pipe size for our system. If you missed that session, no problem. You'll still be able to follow along just fine from here. The HYSYS line sizing manager is a great tool for selecting a pipe size based on basic input information. But when you want to see how the system would actually behave, like reviewing the pressure drop profile or how the flow behaves inside the pipe, you need to run a pipe segment simulation. This is a useful tool for detailed design and designing pipes that will work reliably in the real world. Today, we will use HYSYS to simulate how a pipe segment performs, and we will look at design parameters such as pressure drop and flow velocity. By the end of the session, you'll know how to set up the simulation and make sense of the results and improve your design. Here is a simplified diagram to explain the setup. On the left pressure of 1000 kPa, the pipe runs 350 meters to the heat exchanger, which needs at least 400 kPa as an inlet pressure. As we go through, we will track the flow rates and the pressure profile to ensure that the design works as planned. Once we finish the simulation, we'll go through the results step by step. We will look at the total pressure drop across the pipe, the velocity profile to make sure that it is still within the design limits, the outlet temperature and how it changes along the pipe, the type of flow in the pipe and whether there's a risk for slack flow, energy losses in the system. And finally, we'll check if the selected 50 nominal bore pipe is suitable for the design. This will give us a clear picture of how the pipeline performs under these conditions. Now that we've set up the scenario and goals, let's move over to HYSYS. I'll guide you through the inputs and explain how to interpret the results as we go.
Now that we are here in HYSYS, we'll start first by inserting our components, which is water. We're going to add and search for water. Click on it and then add. And then now we're going to put in the fluid package and then select as steam. There, the green bar shows that everything is in place. Now let's move to the simulation environment. And in the simulation environment, what we're going to do first is to insert the material stream. Just click on the blue icon there and then put it into the simulation environment. Normally what I do, I'll just start by renaming this stream. And I'll call it feed water. We know that the temperature, it's room temperature, 25 degrees. And the supply pressure is 1000 kPa from our problem statement. And the flow rate is 15 cubic meters per hour. And then the program is going to ask us for the composition. So to put in the composition, we go to the composition tab there. We know it is just pure water. So we just type in 1 for the mole fraction there. And then the secondary window comes and we just click on OK. The green bar shows that the material stream is now fully specified. Now, with a fully specified material stream, what we need to do is just to insert the pipe segment. The way to do that is you can come here to the Behaviour palette and search for it. But this is the icon here for a pipe segment, right? If you don't know or you can't find it, you just come and search here, pipe. And then it will pop up. You just click on it and then bring it to the canvas. And then what I normally do, I would just double click on it and then rename it. This one I'll call pipe segments, pipe segment. And then for the inlet and outlet streams, we're going to use this input for the inlet. We will connect it to the feed water stream and it connects to the pipes. And then we've got the outlet or connect the heat exchanger inlet stream. And then the program will tell you that energy stream required, which is this one here, the red one, and call this one PQ. And then the bar at the bottom there, 10TL, that tells you that some information is still missing. And this one here says no segment edit, meaning it's asking for the geometry of the pipe. So to do that, you come to the ratings tab here, sizing, and then append segment. What append segment means is add new segment at the end of the pipe. The append segment. And this is where we're going to put the geometry of the pipe. We know the fitting. So it's called segment 1. The fitting is pipe, and the length is 350 meters. Elevation, we are going to assume the pipe is completely horizontal. There's no elevation change. And then for the outer diameter, you double click here. And then we're going for a schedule 40 pipe. And then the nominal pipe diameter, we remember I said it was about 50 nominal ball. Then you get 50. And then the program will calculate the internal diameter of the pipe, which is 52.5 millimeters. Yeah. And then once you've done that, you've done pretty much the minimum required for the pipe dimensions. However, since this line is a 350 meter line, what I will do is split the line into, say, 10 segments. So the model can calculate every 10 meters. So for this one here, I will break the increments to 35, if that makes sense. And then we'll go and specify the heat transfer information. You come to this drop down here, and then you estimate the heat transfer coefficient. In here, it's the first thing to ask you for the ambient temperature and to demonstrate how the heat transfer actually affects the process. I'll use a slightly lower ambient temperature of 10 degrees. So this is about 15 degrees lower than the process temperature. And then we're going to include the pipe wall thickness in the calculation and include the inner heat transfer coefficient and the outer heat transfer coefficient. For now, we just exclude the insulation. We're not doing insulation calculation here. And then the ambient medium, the pipe is not underground. It is exposed to air. So you click on air, and then it should ask me what is the wind velocity. For our case, we just take 1 meter per second. But if it's in a windy environment, you can change this to whatever the typical velocities are in that region. Now we've got a green bar at the bottom, meaning the minimum information is there.
Okay. With that minimum information, what I'll do is I'll show you that the pipe segment has already converged and we have results. But before we go and do that, I'll just tidy up this model space here for us. I'll put in the tables. Normally that's what I do. I'll just put in tables so I can be able to see what I'm working with here. So I'll just come to the inlet stream or the feed stream, right click on that and then show table. And then in the tables, I will be able to see the temperature, the supply pressure, and the molar flow. But I don't really want to see molar flow. I want to see the volumetric flow. So how I'll do that, I'll just change this to volumetric flow. And click on this and then remove this variable. And then you want to add a variable called volumetric flow. Search for it, volumetric flow. Standard ideal and liquid volume flow. This one here, right? And that should be your 15 cubic meters per hour volumetric flow. There you go. So this is, let me just zoom out a little bit here. This is the process conditions for the feed stream. And then now we want to see what comes out on the other side of the pipe. So right click on that and then show table. Then you'll have the exit temperature, which is about half a degree lower than the inlet temperature. And that is pretty much because of the ambient conditions that we specified. We specified that the ambient conditions was about 10 degrees Celsius and we had a wind speed of about 1 meter per second. So it's affecting the outlet conditions of the water coming out of the pipe. And you can see there as well, the exit pressure is 732 or 733 kPa. We supplied it with 1,000 and then we're getting out 733. That means there is a pressure drop happening in the line, which you would normally expect. Now, let me just change this again to volumetric flow. I will remove the molar flow and then add a standard ideal liquid flow, which is 15 cubic meters per hour. That shouldn't change, right? We're putting in 15 cubic meters per hour, we're getting 15 cubic meters per hour, but the temperature and pressure has changed, right? So in a simple way, this is how you get your results. However, we want to drill a little bit deeper into this, right? And see
all the other parameters like the Reynolds number and all the interesting information about what's happening in the pipe itself. So to do that, you can just double click on the pipe icon and then you go to the performance tab, this one here, right? In the performance tab, you'll see that now, since we've split that line into 35 increments, the calculations are done in a way that the 350 meter pipe is split into 35 sections. And to view all those, we can just come here, so view profile. And then you've got a table. This table has got all the design results that we need. So the first one here, it will be at the pipe length. So you've got 0 meters, 10 meters, 20 meters, 30 meters, all the way to 350. And it will it shows how the pressure drop is also changing, or the pressure is changing within the line. It starts at 1000, and by the time it comes out, it's 733 kPa. So this is your pressure profile across the line. So at any given time, you can say, okay, I wanted to put in a transmitter along that line. Let's just pick this point here. At 170 meters, I wanted to install a transmitter. What will be the pressure at that point? Then you can see that the pressure will be at 170 kPa. And the pressure drop profile, 10 meters, you've got about 7.6 kPa pressure drop. And then the temperature profile as well. It starts at 25 degrees. But because of the ambient conditions are cooler than the process, you start losing energy, and it comes out slightly cooler, but not significant. And then you can do the same for the heat transfer, basically how much heat is being lost to the environment, right? You can see that. And the flow regime, that's what one of the things that we were concerned about. You can see here, it shows that it is liquid only. There's no flashing happening in the line, right? So you got only liquid coming out. And this table, I think it extends beyond this. So these are some of the design parameters that you might be interested in. And this is where you'll find them. Yeah. That's the Reynolds number. We've got the liquid velocity. That's the velocity within the line. So it doesn't change, right? And then one other way to view the results is by using plots. So you just come to plot here. You can see the elevation doesn't change. It's a completely horizontal line. And this is the temperature. The temperature drops from 25 degrees along the pipe length to 24.4 degrees. And you can use these graphs in your report, in your the output, to show that you've considered the temperature, the pressure, the liquid holdup in the line, the Reynolds number, the velocity, and all the other parameters. For the sake of time, I think what I'll do is I will stop here, and then in the next video, I will include fittings into this line, and I'll show you how to model fittings into the line and see the impacts of having those fittings. For example, we'll put in 2 block valves, a flow meter, and maybe an elbow, and see how it affects the pressure drop. Thank you so much for being so attentive. I know this could be a little bit slow for people who already know how to do these things, but slowly but surely we'll get into more complex simulations. Thank you so much, and see you in the next one. Cheers. Bye.